In the kind of calculus that you did in the first semester, you had various ideas. Most of them revolved around graphs that looked like y equal f of x. One of the first calculus problems that we figured out how to do was how to find the equation of a tangent line, which means firstly, we have to know a point on the tangent line, which is no problem if I know the x value, x equals c here, that I'm interested in. But we also need to know the slope of the tangent line, which was not so easy. So in Calculus 1, you figured out that if you calculate the difference between two f values, one evaluated at c, the other at c plus delta x, divide that by delta x, which typically gives you some messy formula that has delta x in it. Take the limit as delta x tends to 0. This is what we're going to call f prime of c, which represents the slope of the tangent line. Other commonly used definitions are dy dx for the first derivative. Second derivative is often written in this way instead of f double prime, and so on. In our new situation, life usually isn't that easy. I'm going to go back and think of that figure 8 shape that we had. It's a nice looking curve. It doesn't have any breaks on it. It doesn't have any sharp corners or anything like that. There is a tangent line at every point on this graph, although you might be concerned about this place where the graph crosses each other. We'll save that for later. At most places on the graphs that we're going to look at, there's a perfectly good tangent line, which then will have either some specific slope or will be vertical. I'm still going to call the slope of the tangent line dy dx. We're going to continue using that symbol, although the way that we're going to get this quantity is considerably different from what we used to. I'm going to think of having some parametric equations that describe some graph, which could turn around and fail the vertical line test in a variety of ways. I'm going to think of having some specific t value, which I'll call t0. That's going to correspond to a point on the graph, which I'll call x0, y0. x0 is f of t0, y0 is g at t0. Now, allow the t to increase in value from t0 to some other value. So at this spot, the t value is going to be t0 plus the amount that I changed the t by. This point is going to have coordinates, which I'll call x1 and y1. x1 and y1 are what I get when I take this new t value and evaluate the f and the g, which are the functions that tell me the x and the y. If I calculate how much the y changed divided by how much the x changed, I'm just going to write down the difference of the y's over the difference of the x's. In order to do this, I've got to assume that the function value at t0 is not identically the same as the function value nearby. We would have ended up having to assume that anyway, so that's not too big of a deal. This doesn't look like anything particularly familiar to us, but we'll do a trick and turn it into something that is. For the fraction on the right, I'm going to divide the top and bottom by the same quantity, which doesn't change the value of the fraction any. I'm going to change it by dividing top and bottom by delta t, which, if you work out the fractions, is the same thing you used to have. What I'm going to call dy dx is going to be the limit of delta y over delta x because everything is in terms of t here, it's the delta t that I have to let approach zero. But if x and y are continuous differentiable functions, then letting the delta t go to zero is the same thing as letting both the delta x and the delta y go to zero. So I'm going to take this limit. Under what circumstances is it okay to take this limit and bust it up into the fraction of these two limits? When both of the limits involved exist and the one on the bottom isn't zero. But if you look at these two limits, that should look awful familiar to you, except for the fact that I'm using the symbol t0 instead of c, and it's delta t instead of delta x, and I have two different functions, one named f and one named g. This should look awful familiar to you. It's the definition of the derivative of something. So if the curve that you're looking at is smooth, that means that both derivatives exist. They're not zero at the same time. Additionally, if we have a situation where dx dt is not zero at the point of interest, that limit on the top was dy dt, and the one on the bottom was dx dt, and this is how we're going to calculate slopes of tangent lines. So for example, let x be t cubed plus 2t plus 1, and y equals sine of t. I'd like to find the equation of the tangent line at the point on the graph that goes with t equals 0. Well, for one thing, I need to know the coordinates of the point on my graph. If t is 0, then x is obviously going to be 1, and sine of 0 is 0. So the point x equal 1, y equal 0 is a point of the tangent line that I'm interested in. In general, dy dx is given by this formula that we figured out. Dy dt is cosine t, and dx dt is 3t squared plus 2. At t equals 0, the top of the fraction, cosine 0, is 1. The bottom of the fraction is 3 times 0 squared, which is 0, plus 2. The slope of the tangent line is 1/2. And then I put that into the point slope form for the equation of a straight line and find out that y minus the known y coordinate is the slope times x minus the known x coordinate. And there's an equation for my tangent line. Notice that if you had tried to eliminate the parameter, it wouldn't have gone very well. If you tried to solve the first equation for t in terms of x, you're going to have to deal with a cubic equation. If you try to solve the second one for t in terms of y, you're going to have to worry about domains and ranges of the arcsine function. So either one of those two approaches is not very good. This is a much better way of thinking about it. Just assuming that your curve is smooth on an interval that contains the point that you're interested in, when you look at this formula, only a few things can happen. POI is short for the point of interest. At the point of interest, if both derivatives are not 0, then I'll calculate the fraction, I'll find out what dy dx is, and there'll be no difficulty. At the point of interest, if dy dt is 0, but dx dt isn't, that means on the tangent line, the y coordinates never change their value as I change the t around, but the x's do. That gives me a horizontal tangent line. At the point of interest, if dy dt is not 0, but dx dt is, that means x never changes, but y does. So that tells me I have a vertical tangent line at that spot. And this ghostly fourth possibility, what if both derivatives were zero at the same time at the point of interest? For a smooth curve, that can't happen. So if we restrict our attention to smooth curves, we don't have to worry about possibility number 4. So suppose that x is t cubed minus 2t squared plus t plus 1, and y is t cubed plus 5t squared plus 1. Using the ideas that we've just previously mentioned, I can immediately write down a formula for dy dx in terms of t. I calculate dy dt and divide it by dx dt. Now, I've got to be careful about some things. When is the dy dt going to be 0? When is the dx dt going to be 0? So write out formulas for dx dt and dy dt. When is dx dt going to be 0? When is 3t squared minus 4t plus 1 0? That's a quadratic equation. I can use the quadratic formula, and after a little bit of work, it turns out dx dt is 0 when t is 1, also when t is 1/3. When is dy dt 0? dy dt is 3t squared plus 10t. That's even easier than the other one. If I want to find out where dy dt is 0, I have something that I can factor a t out of. dy dt is 0 when t is 0 or when t is negative 10/3. The only really bad situation that I could have would be if there was a t number where dx dt and dy dt were 0 at the same time. The only place where dx dt can be 0 is 1 and 3. T equal 1 is not one of the places where dy dt can be 0. T equal 1/3 is not one of those places either. Dy dt is 0 at t equals 0, which is not one of the places where dx dt can be 0. And looking at t equals negative 10/3, that's not on the list of places where dx dt can be 0. So dx dt and dy dt are never 0 at the same t value, so everything's fine. Also, in view of what we said on the previous page, you're going to get a horizontal tangent line in this case when dy dt is 0, which are those t values. You're going to get a vertical tangent line at places where dx dt is 0, which we now know as well. If you wanted to, you could take t equals 0, put it into the formulas for x and y, and you would have actual xy coordinates of a point where you had a horizontal tangent line. You could do the same thing with negative 10/3. If you're looking for actual coordinates of places where you have a vertical tangent line, you would plug t equal 1 into those formulas, get a point, plug t equal 1/3 into this formula, get another point. So we can easily identify places where vertical or horizontal tangent lines occur if our curve is smooth. This result that we've got, dy dx equals dy dt divided by dx dt, which looks like a fraction of fractions but isn't one. We can think literally of this as calculating the slope of the tangent line, but there's another way we could think. This says that the way I do derivative with respect to x of the quantity y, and then when you look over here on the other side of the equation, y only shows up in that derivative in the numerator of the fraction. The way you do d over dx of something is this. You do d over dt of the something divided by dx dt. The something really is just a bookmark. You could put anything inside these parentheses, and as long as you put the same thing in both parentheses, the statement would still be true. So I'm going to make up my standard nonsense symbol. The derivative with respect to x of smiley face is derivative with respect to t of smiley face divided by dx dt. And really, I don't care what smiley face is. If smiley face is y, we get back this formula that we've developed. If it's something else, then maybe we're calculating something else. So we're going to take this equation as being a general principle. If smiley face is y, as we said, we get back this formula that we already know. What if I make the smiley face equal to dy dx? Then I'm calculating the derivative with respect to x of dy dx, which according to the smiley face formula ought to be the derivative with respect to t of dy dx divided by dx dt. The derivative of y with respect to x both times is the second derivative of y with respect to x. So if I know how to calculate dy dx in terms of t, I'll know how to calculate the second derivative in terms of t also. Having done that, what if I then choose to make smiley face equal to the second derivative of y with respect to x? Then I'm going to be calculating the derivative with respect to x of the second derivative of y with respect to x, which would be the third derivative of y with respect to x. And following the smiley face formula, this will be the derivative with respect to t of the second derivative of y with respect to x divided by dx dt. It may be disturbing to see derivatives with respect to both t and x running around in this thing, but that's no problem. When we figure out dy dx, dy dt and dx dt are functions of t. So when I do this derivative, for instance, it's the derivative with respect to t of some formula that just has t in it. So you see, there's really no problem with this. So for example, let's let x equals 2t plus cosine t and y equals 2t minus sine t. I want to find formulas for the slope of the tangent line and the concavity on this graph in terms of the t variable. dy dt is straightforward. That's going to be dy dt over dx dt. Derivative of y is 2 minus derivative of sine t is cosine t. I got to divide that by the derivative of x with respect to t. Derivative of 2t is 2 plus the derivative of cosine t is negative sine t. So in terms of t, dy dx is 2 minus cosine t divided by 2 minus sine t. If I want to calculate the second derivative, I've got to take the derivative with respect to t of dy dx, which we just figured out a moment ago. I have to figure this derivative, and then I have to divide that by dx dt, which we've already calculated once when we did the first derivative. So I'll just write the answer down again. This is a little messy. You're going to have to use the quotient rule on it, which says that the derivative of a fraction is the bottom times the derivative of the top minus the top times the derivative of the bottom divided divided by the bottom squared. So I've just written out the quotient rule here. There's going to be some simplifying and rearranging to do, but it's just a matter of algebra and some trig identities. In the end, I get a formula for the concavity based on t. Oh, and also notice that neither dx dt or dy dt can ever be zero. For instance, sine of t never gets as big as 2, so I don't have to worry about that sort of issue. Even though I don't know what that graph looks like, I can ask myself, are there any potential points that might be inflection points? Now, the inflection point is a place where the second derivative of y with respect to x is 0 or undefined, and on one side the graph is concave up, and the other side it's concave down. The second derivative makes sense no matter what t-value you put into it, so I only have to worry about the case where the second derivative of y with respect to x is 0. When a fraction is equal to 0, that means the top of the fraction is 0. So if I'm going to have any candidates for inflection points whatsoever, the t-value that goes with them will have to obey 2 sine t plus 2 cosine t minus 1 equals 0. I decided to be extremely lazy and solve this on the interval from 0 to 2 pi using my calculator. The results of that were t was 1.9948 radians, or t equals 5.85915 radians, assuming I'm interpreting the t as an angle, or maybe it's 1.9948 seconds if I'm thinking of t as being time. In any case, the picture has only 2 places where it could conceivably change its concavity. I want to return to that figure 8 graph that we looked at previously. X equals 5 times sine of 2 times t, y equal 10 cosine t. You'll notice there are points of the graph at the origin. I want to figure out the slope of the tangent line there, or more accurately, slopes of tangent lines, because there's more than one of them. First thing I have to do is identify what t values are going to land me at the origin. Now, I have trig functions here. Sine of something equals 0 only happens when the something is a multiple of pi. Cosine of something equals 0 only happens when the something is an odd multiple of pi over 2. So for the first case, this leads to 2t has to be a multiple of pi. There's no t in that second equation, no 2 in that second equation though. So for 10 cosine t equals 0, t has to be an odd multiple of pi over 2. The first one says t has to be a multiple of pi over 2. The second one insists not only that, but t has to be an odd multiple of pi over 2. So the places where I'm going to land at the origin are going to be odd multiples of pi over 2. Pi over 2 is about 1.57. So if I want to think about the graph that's close to that t value, I should have beginning and ending t limits that are close to 1.57. Having put my functions in, I've adjusted my window to start at t equals 1.4 and end at t equal 1.7. I had to experiment around a little bit to find window settings that would give me a nice representative picture of what I'm interested in and not anything else. Using these window settings, if you draw the graph, you get this picture. So close to pi over 2, t equal pi over 2, that is, the graph is sloping upwards, which I'll symbolize by drawing this graph in. Now, the other one, t equal 3 pi over 2, that's going to be about 4.71. I want you to believe I'm not cheating or anything here. Same formulas. All I'm going to do is change the window. I'm going to change the smallest min value for t. I'm going to make that 4.6. And I'll make the biggest t value 4.9, and then draw the graph. And see, I pass through the origin on a decreasing height graph this time, which I'll symbolize this way. The next bigger odd multiple of pi over 2 would be 5 pi over 2, but that's bigger than 2 pi, and I'm only looking for t numbers in the interval from 0 to 2 pi here. So I've shaded in the part of the graph I'm interested in that goes with the t equals 2 pi, pardon me, pi over 2. So even though I'm sitting at the origin in both cases, I'm doing that at different time values, assuming the t is time, or different angle values if t is an angle. For the one that we started off with, I'll have an upward sloping tangent line, and the other one, I'll have a downward sloping tangent line. If I use our formula idea to calculate dy dx at t equal pi over 2, after the dust finally settles, I find out that the slope is 1, so the tangent line should be sloping upwards, which is what we saw. At t equal 3 pi over 2, doing the arithmetic, the slope of the tangent line, which we're still calling dy dx, even though we're not getting it the way we used to, is negative 1, which means I should have a downward sloping tangent line. These are consistent with the observations that we've made about the graph. Lastly, I want to look at arc length. Because of the new way that we're describing these parametric curves, we need to be a little bit careful about what we mean about subintervals and so on. We're going to start off on our curve at some particular t value, t equals a, and end at t equal b. I'm going to think about the interval of t numbers from a to b, and I'm going to divide that up into a number of smaller subintervals of t values now. So this is t equals a, which back in chapter 7 we would call t number 0. This is the point on the graph that corresponds to t number 1. This is the spot on the graph that corresponds to t number 2, t3, and so on. T equals t number n is the end point. Every one of these points has a t value to go with it. And knowing the t value, for instance, t equal a, lets me calculate x as being f of a and y as being g of a. The same sort of thing is true all the way along the curve until I get to the end. The x-coordinate of the end point is f of b. The y-coordinate is g of b. The setup that I'm using here is exactly the same setup we used in chapter 7, over and over again. So it should be familiar to you. If it's not, be sure to look back at it. Nothing new is going on here. If I look at the distance along subinterval number I have to take delta x squared and delta y squared add them up, and then take the square root. But the change in x is the x-coordinate at the end of subinterval number I minus the x-coordinate at the start, y at the end, y at the start of subinterval number I. This is just the Pythagorean theorem again. And not to stretch this out any longer than it needs to, underneath the radical sign, factor out delta t squared, and then break the thing up into the square root of this quantity times the square root of delta t squared. Since delta t is always taken to be positive, square root of delta t squared is just delta t. Then we would add up all such things and take the limit as delta t tends to 0. This is change in x over change in t. The limit of that as delta t goes to 0 is the derivative of x with respect to t. Likewise, the limit of that is the derivative of y with respect to t. This is an almost exact analog to the formula we had back in chapter 7, except now it's not y as a function of x, or even x as a function of y. It's x as a function of t, and y as a function of t. Notice if you pretend that this is a number, and that these things are fractions, none of which are true, if you algebraically simplified this, it would just turn into the Pythagorean theorem again. I want to try this idea out on something that I already know the answer to. I'm going to look at a circle, center at the origin, radius b, where b is some positive number. One way to parameterize this is x equals b cosine t, y equal b sine t. I'm thinking of t as being the angle now, and I've got to let t go all the way around 0 to 2 pi in order to get the complete circle. The derivative of x with respect to t is negative b sine t. Derivative of y with respect to t is b times cosine t. I've got to square the derivatives and add them up, and then do the square root. Underneath the radical sign, a clever person will notice that they can factor out of b squared. Sine squared of t plus cosine squared of t is 1. Square root of b squared is b, because b is positive, so I just have to integrate a constant. Antiderivative is b times t. Put t equals 0 and t equal 2 pi into it. The circumference of a circle of radius b, using parametric form now, is 2 times pi times the radius, just as it's supposed to be. As a much less nice example, I'm going to look at that figure 8 graph that we talked about previously. X is going to be 5 times sine of 2t. Y is going to be 10 times cosine t. T goes from 0 to 2 pi. Calculate the derivatives. For dx dt, I had to use the chain rule. The derivative of sine of 2 times t is cosine of 2 times t times the derivative of 2 times t. That's where the extra factor of 2 comes from. This is just cosine of t, so there is no extra factor of 2. Then integrate from 0 to 2 pi the square root of what you get when you square dx dt plus what you get when you square dy dt. Since that's a very ugly looking integral, I pulled my calculator out, and it turns out that the circumference of this figure 8 shape is about 60.9722 units of distance, whichever system of units that you're using. The discussion of parametric equations will be very important to us if you go on and take the third semester calculus course. When we get to vector valued functions in that course, if you understand about parametric equations, the basic ideas will not be very complicated for you. Coming up next, polar coordinates.